You are very much audible, sir.
Okay. So the topics are MEMS pressure sensors for entire range from low pressure, high pressure, 150 millibar, 10 bar, and also to high 1 bar and 400 bar, very high pressure.
Very skeptics, man.
Hello. Also, I'll show you how to integrate along with this mechanical component on chip. Okay. So to just have this clean, 1 atmosphere is called 1 bar. It's also called 760 millimeter of mercury. If you want to know more, blood pressure is 120 by 80 millimeter of mercury. So atmospheric pressure is 1 bar or 760 torr or 760 millimeter of mercury. This is for memory. First of all, everybody's mind comes, why do we need to miniaturize these sensors? You don't need to miniaturize if it's a big hall or big thing, something. Supposing you want to have access to the intracranial pressure, if you want to monitor, you have to drill a hole. You see the head here, the hole is drilled. In fact, I had the good fortune of seeing this operation being done in Nimans, along with Professor Nokant and some of my students a few years back, because they wanted us to make this sensor. So we have made it, but there are some issues which have to be biocompatible, etc. So what is this intracranial pressure? That is about normal pressure inside is 15 millimeter of mercury. So if there is a, these days you know that in Bangalore every day there are 2 to 3 dozens of road accidents taking place, motorbike. You have seen the young kids going up and down on the one wheel, then getting into trouble. So in the road accident, when that happens, if there's a head injury, the pressure inside the intracranial goes up. What was 15 millimeter of mercury goes up 16, 17, 20. And if it goes to 35 millimeter of mercury, he has got terrific headache and he becomes unconscious, he or she. In fact, you know, when you go for exams, you get headache. Why? Because the pressure inside goes up. The intracranial pressure goes up. So when they go to the demands of the National Institute of Mental Health and Neurosciences, the first thing that I saw that operation taking place, now competent myself, a small hole. You must be able to insert your sensor through that. So that's why you need to do the miniaturization. And the sensor should be biocompatible. Silicon is good, and anything you put on the coating of paraffin or so, which is biocompatible. So intracranial pressure is 15 millimeters, 35 millimeters. It's low pressure sensor. For Nimans, we were working on that. We have done sensors. We have that instability problem because of water, etc. Some coatings we have to. Next, blood pressure. This also is another project that we have just taken up now. This one. This is 80 by 120 millimeter mercury. Now, if there's a block, you can just touch it by putting a sensor and put it in through the artery or whatever nerves and see the pressure. If there is some pressure rise, push the catheter with the sensor there. If there's a pressure buildup, that means there's a blockage. That means you would need to go bursting the block. You can do right there. This is another project which we are on. Because you can see when you make this device, it's terrible. You have to device chip size to be very small, some microns, 150 microns and all that. So it becomes horrendous, difficult job to fabricate, process and everything. We are at that. Some of my good students are there who are working on that. I don't go to the lab. Okay, I sit on the chair and guide them. Okay, so that is the way I operate. So these days I'm operating from home. So the size of this IC chip should be inserted is very small. Okay, and it should be biocompatible. Now, oceanography. Other application is the aeroplane. Okay, In aeroplane, you need to monitor the height and also the speed with which the aeroplane or helicopter goes. So you put a sensor there. As you go up there, the pressure is very low. So you need to have a very low pressure sensor, maybe 100 millibar or even smaller than that. So that sensor requires low pressure. One more sensor that you need is, so that one will be absolute pressure. There is one more is the differential pressure. You put at the near the engine, you put it there, and then the pressure difference between the height and the pressure due to the velocity, the difference gives you the speed. So for this, we have made these devices and sometimes they have been put in helicopter. So that is the pride of the place. In the AAC, we are giving to the HAL regularly these sensors. So you can believe that in India we can make these sensors, and if you import, they will ask horrendous price. Then oceanography also, see, you can finish the human head, then the helicopter, and the aircraft. Oceanography also, the sensor if you want to measure the depth. In fact, as you go below the water, you go 10 meters below in the water, 1 bar, 1 atmosphere pressure goes up. If you go 100 meters, that is 10 bar atmosphere. You can see that that's why you begin to feel the pressure there. People want to see below oceanography, they have to have some sensors. And that should not get, that should have protection against all this, salt, salt, etc. Okay, so now let's demonstrate to the subject. This is a very simple device. Okay, all we need to do is, see here, this is the device. This is a silicon chip in which on the top surface, in fact, it is a combination of resistors to form a Wheatstone bridge with balanced conditions. Now, if that Wheatstone bridge experiences some pressure, stress, then the resistances change and it gives an output. Simple theory of piezoresistor pressure sensor. To that pressure, that is the pressure sensor is this. So this is the chip surface is here. This is the anchor, and you can see the gap here. That is actually a cavity which is exposed to the pressure port. So it is, once you make the chip, I'll tell you how to make or what are things in that. Once you have this chip, mount it on the header. You can see the portion, and afterwards you can close it with the header cap. So when you header, and have the atmospheric pressure, or you can close it with vacuum there. So depending upon that, you call it as absolute, gauge, you can call. So if it is zero pressure, in the mounted tube there, you put the cap on the tube, it is absolute. And if you have air there, atmospheric pressure, when you put the cap, it is gauge. Now we'll show you one by one. So before you go further, the pressure, I think even before I was born, this theory was there. Okay, in IAC, when I studied in the E department, there they were projecting these equations. I said, why are they projecting? Now I know I'm living with that. Okay, so pressure is H is the thickness of the diaphragm. A is the half width of the diaphragm, square diaphragm. W0 is the reflection when the pressure comes in on the diaphragm. Okay, so this equation relates the pressure to the deflection. Okay, now note that the deflection of this diaphragm should be small compared to the thickness, at least 1/10 of that. If I have 20 micron thick diaphragm, I can deflect right up to that. Why do I want W0 to be small compared to H? Look at the equation. It's an linear equation. If W0 becomes larger, so W0 should be small compared to H. With 20 micron, it is better be a 1 micron. That means the pressure at which you want to sense what the thickness and the dimensions of this diaphragm are to be chosen. Okay, so this is the general size. Now I'll go one by one. diaphragm H is diaphragm thickness, 2A is the diaphragm dimensions, square. It is the other way it becomes square. So this is the pressure port here. This is the cap. Are you able to see? I hope you are able to see my cursor. Okay. Go one by one. Pressure sensor types. Absolute pressure sensor, gauge pressure sensor, differential. Absolute is when you put the cap, there is vacuum. Okay, this slide you have already seen. This vacuum, so there is the absolute pressure sensor. Its application is atmospheric pressure measurement, and also in the mountain height, if you want to monitor, that will all be the other side of the diaphragm will be experiencing vacuum. This is the pressure port where it sees what is the pressure outside there. That is the absolute. When you put this cap on the top, after mounting the die, etc., when you put in the header, it is done in the atmospheric pressure. That means what you are measuring is with respect to the atmospheric pressure. Gauge atmosphere. This is the one which is used for blood pressure monitoring, etc. This is used. I told you, put it in the aircraft to see the measure of the speed. Beta tube. Inside the beta tube of the helicopter or aircraft, there will always be this sensor. It will pressure 1 is actually the pressure 2 gives you the differential due to the speed and the height. So the differential pressure tells you what is the speed of, remove the heights corresponding to that. It gives you the actual speed of the device. On the wings, you may put an absolute sensor. Okay, so there are two sensors in the aircraft right there. So now you can see this is one diagram which is stole from somewhere. Put it here. So this looked good. See, this is the diaphragm. It's a cut open sensor. It's a diaphragm, and you can see the cavity. And you can see bottom side, I can bond a glass to that. Just by fusion bonding technique, bond glass to put the glass together, apply voltage, it will bond. It is magic. Okay. Actually, movement of sodium ions from glass to silicon, it creates an electrostatic field and it gets bonded there. Now, this is, you can see the cavities here. So, all that you are monitoring, as I told you already, is deflection in the diaphragm. And deflection in the diaphragm can be monitored. There is no electric effect. That means, on the, for your information, on the top of the diaphragm, you can put lead zirconium titanate is a T piezoelectric. So when it experiences stress, voltage from that is the property of piezoelectric material is a T. T can work only if there is dynamic pressure. If it is static, it is like it will discharge. So it is stable. So PZT cannot be used for static pressure, only for dynamic pressures. And also it's not compatible with electronics technology. It is a separate beast coming and sitting there on your chip. You don't want it. The other one is capacitive, where you measure the capacity and the bottom electrode. So you can see capacity proportional to epsilon 0 to A divided by D. Every one of us knows this formula. Now the D is the one which changes the effect. But unfortunately, it is 1 by D, so it becomes nonlinear. In terms of this capacitance, if you are monitoring the area, how can you monitor the area? If there are two diaphragms, a diaphragm goes on bending down. Bottom, if you have oxide, the bottom, the top diaphragm can touch the bottom diaphragm. There will not be short circuit. There will be some maximum capacitance. You don't make use of that. You press it further, the diaphragm will start touching everywhere else on the oxide. That means the area is increasing. That will be linear. So this is how they use. It's complicated. But all these are not compatible with the integrated technology. If you want to integrate, you have to go to piezoresistive. Put resistance. We'll see those things now. So go take discussions on the piezoresistive, because everybody likes to go for piezoresistive. Now, when you talk piezoresistive, on the diaphragm, you keep these 4 resistors and connect it in the form of resistance with balanced one. Once the balance is disturbed, and you get an output voltage. So ultimately, you get pressure versus output voltage. Okay. Now, it's easy to embed. You can silicon diaphragm you can use. Why do you want to use silicon? Silicon has got very high Young's modules. Gauge factor is very good in that. So if there is deflection or stress, it will give very good output. And silicon is also compatible with the VLSI technology. All that physics people, electronic people, everybody loves silicon material. Okay. So we take a look at these silicon-based piezoresistors. That is silicon diaphragm. On the top of it, you implant a resistor. You do the resistor by an implantation, or by carrying out a diffusion process, where you can transport some gases, put diborane there. That will do the dope thing. Okay. So you have got this is one resistor which is parallel to the edge of the diaphragm. Another resistor perpendicular to the edge of the diaphragm, square diaphragm. So if a from top, there will be deflection downward. That means this resistor is experiencing a longitudinal stress and strain. If you a resistor and stretch, length will increase, it will decrease, resistance will go up. But here, more, that's not where the resistance. The resistance also, resistivity also changes. It means the resistance of the material silicon will change. H factor something like 80 or 100. So this, when you touch it longitudinal direction, the resistance will go up. This is experiencing transfer stress. This one. So the equivalent of area decreasing, but the resistance decreases. So this the resistance will go down. Initially, you design that output 0 when the pressure is 0. Now, when the between the two resistors change, you get the output voltage. That's the principle. Okay. To our bridge diaphragm, to our perpendicular. That's all simple there. Now, a parameter called gauge. I'm not going through this derivation. This slides are with you. You can take a look. Or any book gives this thing. The gauge factor is a term that one always say, I want a material which has got very high gauge factor. That's why I want silicon. You subject it to stress. R changes by delta R due to a strain epsilon. Stress by strain is Young's modulus. Okay, so this has high Young's modulus, and this gauge factor is actually large in the case of silicon, 80 to 100. So delta R by R by strain will give a gauge factor of 100 for a particular strain. So you should go on increasing the change in the resistance to get higher and higher gauge factor. This is the principle. Nu is the L and width changing, that is very small. So major component giving rise to piezoresistivity is delta rho by rho, that is delta R by R. Rho resistivity itself changes due to the mobility changing in the silicon. Whole mobility. In fact, if you want to think in terms of physical, no abstract, the whole, if it is a N-type silicon, there are free electrons. Okay, they are very difficult to separate them. Gauge factor is small. If it is holes, holes are there, vacancies are there. Holes moving means vacancies move. That means the electron has to jump from one point to another point. So if I separate the distance between them by touching, the distance required for jumping increases. That means the resistance increases. It's a very crude way of thinking. No quantum mechanics. Okay. Jumping distance for the moves. Actually, whole movement is jumping electrons from one vacancy to one vacancy. So that increases, therefore resistance increases. That's why you take N-type material, P-type material as the sensor. So when you want to put a P-type material on the diaphragm, you want all the four resistors to be isolated. So you do is take an N-type substrate, on that you or diffuse four resistors on the top, then the isolated energies on each other, because you know PN junction there is a barrier. So it is a PN, etc. So there is all the devices are isolated from each other. You can make a disturbance. Now the gauge factor is metals. It is, you may ask, metal can also be used as a gauge. The gauge factor is very low. That number that I put there. Silicon 80 to 120, N-type will be much lower. Polycrystalline silicon also has gauge factor. It's about 30. People try polycrystalline silicon by depositing resistors on oxide, so that resistors are totally isolated for high temperature, etc. They can use, but gauge factor is low. So normally you use resistor, but we'll see how to go through that. Mu P is the mobility. Rho is 1 by charge. P is the whole concentration, that's equal to P concentration. Mu P is the mobility, of course. It is actually the mobility which is changing. Okay, mobility falling, so rho increasing in your test. Now, this is what I have been telling. The diaphragm on the silicon. Okay, but I don't think you have it in the slide that I have sent there, because last minute I thought there would be some difficulties, so I put it. So 4 resistors R1, R2, R3, and the diaphragm is like square. So R1 and R, if I present is perpendicular to this diagram, R1 and R3, the diaphragm will go inside. So R1 and R3 will increase in resistance to the gauge factor. The strain, delta R by R will strain. R2 and R4 will lateral transfers, so it will go down. Simple way of thinking is one is length increasing, other one is width increasing. I have to know physics for that. Okay, so on the chip itself, lines will be all outside. This will be soon. See, if I pressurize in the plane of this surface, R1, I am not able to see you or listen to you. R1 will go because it extends. So R1 plus delta R plus delta R, that will go up. And R3, opposite term also go up by delta R. R2, which is actually parallel, transverse its experiences. So R2 will become delta R, this will become dr. Fortunately, all these four the stress will practically be the same if I keep it at the center. Center means the edge center. So all will be delta R by R. So what will be the output voltage? When it's balanced, output voltage is 0. And when you get an output, it is R plus delta R by 2R minus that. That is input voltage into delta R by R. That is the output. That is for simple theory. So delta R by R is related to gauge factor. Gauge factor into strain is delta R by R. So the put. Here, if you understood it, there is nothing more. I can go ahead with the thing, zip some of the technology things very easily. I already spent half an hour. Okay. 4 p-type resistors are put like this. Now let's go further down. See, this is only one diaphragm I have shown here. Next slide 13. I am showing this. I have run myself. I have run the full silicon wafer. You can see there is a flat here. Okay. This flat here is a particular direction, 100 direction.
Sir, slides are not changing, sir. Hello.
Pardon?
Sir, slides are not changing, sir.
Oh, slides are not saying.
Yeah, sir.
I am now in the P-type register slide.
So now 10 receive. Okay, sir.
I'll change. I'll wait.
Okay, sir. Continue, sir. Okay.
Is it okay?
Okay, sir. Okay, sir.
Very good. See?
Yeah, sir.
Yeah.
You can continue, sir.
Big silicon wafer is sitting there. Okay? You are seeing the silicon wafer.
No, sir. Slide number, which slide number is, sir? Now is slide number showing 10. 10.
No, that may be different. I don't have it in your slide there.
Sir, we are looking at slide number 10 now.
No, I have gone this what I'm putting now. What is number there? What you are seeing it in your slide. But in my slide, are you not able to see?
No, sir. Only you are seeing page number 10, slide number 10 only, sir. You are seeing.
Oh, I see. I think I changed the slides, modified. I put the extra slide. Okay, but I thought I would be visible here.
Otherwise, Prasanna Kumar,
Yeah, sir.
you take over. You start sharing the slides. And
It's
as
there,
soon as the
sir.
professor completes it,
Okay,
sir,
sir.
but sir, Professor Kane, but sir, once
Yes.
the slide is done, you just say next slide. We will bring the next slide.
I'll keep it open here.
Okay, sir. You can continue.
I can continue?
Yeah, continue, sir. Continue.
I'm on 11th slide now.
Please go to the 11th slide, sir. You are still in 10th slide.
10th is that.
10th is done.
See, your old slide advertisement cannot match with this. I thought you are going to share this slide.
Okay, sir. But sir,
yes,
you please stop sharing the screen. You please stop sharing the screen. We will start sharing the screen ourselves. We will do that for you, sir.
Oh, I see.
You please stop sharing. Stop sharing. There is a button, stop sharing.
Stop sharing.
Yeah, stop sharing. You please do that, sir.
Stop sharing.
No, not yet done. HPK.
Okay, now.
Yeah, sir. Trying that one, sir. But sir, you have to come out from the sharing, sir. Then only I'll go into that one.
Sir, there is a share button here at the bottom of your screen.
I've done that actually.
You say stop sharing.
Stop sharing.
Now it is done. Now it is done. Thank you, sir. Now it is done. Now HPK has started sharing the content. Yes.
Now I'll go to my slide.
Sir, you don't, sir. But sir, please do not do anything, sir. We will do that.
No, but I have seen my slides.
Which slide you want, sir? Now.
Now it is 11th.
11th. Okay. HBK, go to slide 4 now. We are on 11th slide. Go to slide 4.
Shall I open the slide?
Okay, sir. Now? Yeah.
Now we are on slide 11.
This is 11.
Okay, sir. Professor, but sir, once you are done with a slide, you please say next slide. Then the next slide will come.
Actually, no, sir. I am opening the PPT.
Pardon, sir? No. Please don't do anything, sir. You please, you will. Are you seeing the slides on your screen, sir?
I'm seeing slide number 11.
Please go ahead, sir. Please go ahead. Once you are done with a particular slide, please say next slide. Then the next slide will come up for you. Then you can proceed.
I don't have to do the slideshow.
We will have this protocol. We will have this protocol, sir.
Okay. Harish, I'm not putting the PP. I'm putting only the minimized version.
No, you please don't put anything, sir. You please don't put anything. Slides will keep coming up. You can speak over that on that.
Supposing
you continue with your lecture.
No, if I put slideshow, will it be all right? No.
No, okay. I didn't get you, sir. Slide is visible. You please continue, sir.
Next slide.
Next slide. HPK, go to slide 12.
But I have to change. Okay. So in this slide, you see the wafer. So
Hello.
do you see the wafer?
We see the wafer now.
This one, no, sir. Sir.
Correct. Exactly.
Okay,
Yes,
sir.
yes.
So shall I put it, take it and display? Okay. So I'm seeing. Okay, now. Okay.
Yeah, sir. Yeah, sir. You can continue. Yeah, sir. Yeah, sir. You can continue, sir.
Okay, we are in sync now. We are in sync. So top view of the wafer. Go back to the slide, please. Go to the.
So slide number is now 14. Hello. Hello.
Sir?
Sir, mute ಮಾಡ್ಕೊಂಡಿದ್ದಾರೆ ಅವರು.
Professor, sir?
Hello.
Sir, please unmute yourself, sir. HPK, ನೀವೇ ಮಾಡಿ.
ನನಗೆ ಕಂಟ್ರೋಲ್ ಬರ್ತಾ ಇಲ್ಲ. ಅವ್ರಿಗೆ ಇದು ಸ್ಲೈಡ್ ಆಪರೇಷನ್ ಮಾಡ್ತಾ ಇದ್ದಾನಲ್ಲ, ಅವ್ರಿಗೆ ಹೋಗಿದೆ ಈಗ. ಸರ್ ಅನ್ಮ್ಯೂಟ್ ಮಾಡ್ಕೊಳ್ಳಿ ಕೇಳಿ ಸರ್ ಅವ್ರಿಗೆ.
Sir, Professor Bhatt, sir, please unmute yourself.
ಹಲೋ. ಸರ್ ಅನ್ಮ್ಯೂಟ್ ಆಗ್ತಾ ಇಲ್ಲ ಅವ್ರದ್ದು, ಮಾಡಕ್ ಕೇಳ್ಕೊಳ್ಳಿ ಸರ್ ಆಗ್ಲೇ ಅವ್ರಿಗೆನ.
ನಿಮಿಷ.
ಅವ್ರಿಗೆ ಫೋನ್ ಮಾಡಿ ಹೇಳಿ, ಮೋಸ್ಟ್ ಅವ್ರಿಗೆ ಗೊತ್ತಾಗ್ತಾ ಇಲ್ಲ.
ಹೇಳ್ತಾರೆ ಸರ್. BPH ಹೇಳ್ತಾರೆ.
I will calling. I'm calling now.
Okay.
Sir, ನೀವು unmute ಮಾಡಬೇಕು sir. Because you are not audible now. You are not audible to us. ಕೆಳಗಡೆ at the bottom of the screen there is. You please close your slide, sir. Yes, sir. Slides will come up on screen for you to speak. And there is a button at the bottom. Unmute. You should unmute yourself. No, are you seeing a mic with a green thing? You press that button. You press the button now. Press that button, sir. Press that button.
Okay. Able to hear now?
Yes, sir.
Yes, sir. We are able to hear you, sir. Please continue, sir.
Okay. Now what do I do? You are sharing now.
Yes.
So
Sir,
I have to go
we
on.
are sharing the, sir, Professor Bhatt, sir, we will share the slides for you. Do anything about it. You please continue to speak. You don't have to do anything. You don't have to do anything, sir. Are you? Is the slides visible to you, sir?
Yeah, actually, I have visible. I'm not able to change.
You're not able to see the slide?
I'm able to see.
But I am going to change this, sir. You don't worry about it. Tell me about next slide.
Okay, let us see.
Okay.
Shall we go to the next slide, sir?
One minute.
Okay.
There is some. Is there a course? Oh. Okay. This is actually the wafer in which there is all dyes are there. Hello.
Yes, sir.
Audible.
Sir, you are audible. Please continue, sir.
Okay. So I am seeing the silicon wafer with a flat there.
Right.
That slide.
HPK, go to the next slide now.
Yeah, sir. Slide.
See, this is the chip. See, in the previous slide, you saw the number of chips are there. That is diced, and that is put here on the header. Are you able to see this slide?
Yes, sir. Yes, sir. You are visible.
Okay. So you can see the wire body and the chip, and you can see the glue by which it's put there. And just 1 minute, I am able to. Okay. Okay. So this is the, I see some blocks here. Full screen. Full screen. Okay. I'll make full screen. Yes. But you think about it. Okay. Right. So shall I go? Next slide.
Yes, sir.
So you can see previous slide you had actually the die there mounted on the header. Now I put a cap there. This is the hole that you see there is the pressure port. Next slide, please. Next. See, you can see something is blocking here. Oh,
so this one or this one or this one, sir?
No. Okay. Can you go back?
Yes, sir.
Yes. So here you can see the stress distribution and all the things. At the edges it is higher. Sir, I am not able to see from half of my screen.
Half of your screen. But you are seeing, sir?
Huh?
I'll transfer. You can change now, sir. You can.
I can change that.
Okay, you can do that one, sir. I'll allow you to.
There is a gray color. HPK. There is a gray color patches on the screen, on the slides. Can you remove that? Yes, sir. Yes, sir. Please tell me, sir.
See on the screen the device which is mounted with the cap.
Correct.
But there is something coming blocking on the right side corner.
Right side corner.
Ghost.
What is that patches?
Now it's clear, sir.
Can you remove that?
Yes, sir.
No.
That is moved out.
Yes, cleaned out.
And
yes.
Your name DH also.
No issues.
Okay, let's go. So this slide is the one where the cap is put. Am I right?
Yes, sir. Yes, sir.
I thought we were able to do. I was comfortable with that. Okay, next slide, please. This is the device which is ready to be put anywhere you want to put. Now, this slide has the, I am reading medium pressure. Okay. Okay. Stress on the red line down. Are you able to see the slide?
Yes, sir.
Longitudinal stress along the dotted line. Okay. So you can see the arrow is put on the left-hand side square diaphragm. That is actually the stress on the square. If the diaphragm is rectangular like this, then the stress at the edge keeps on increasing. Okay. So what I am trying to point out is if you have a square diaphragm of 500 by 500, whatever pressure that you had, 3 bar, it gets magnified by the ratio A by H whole square, a factor of 100 or so. So stress goes up very much in the diaphragm. Next slide, please. Okay,
yes,
you can skip this. Next slide. Okay. Now, go back. One slide back. 18.
18. This one.
19. Go one side forward.
Yeah, 19
okay.
now.
Okay. See, this is, you are seeing there, the blue thing is actually the cross section of the diaphragm. H is the thickness, L is the size of the square diaphragm. So area is L squared. H is the thickness. Now, what we are trying to do is, if the high pressure is high, naturally you have to go to thicker and thicker diaphragm. Because if it is very thin, when high pressure comes, it will deflect quite a bit. And if the deflection becomes comparable to the thickness of the diaphragm, then onwards, it becomes nonlinear. We want it to remain in the linear region, so we are choosing thicker diaphragms. So if I use thicker diaphragm, okay, that is, here is H. Are you able to see my cursor? No? H is there. Oh, no, don't change.
Okay, sir. Okay, sir.
So H is there. Length of the diaphragm is there, L square. Now, if you see the H by, if you make thicker and thicker diaphragm, okay, the peak pressure moves out of the diaphragm. It is outside the diaphragm. See, what I'm trying to point out is, if you have a thicker diaphragm, depending upon how much is the area, H divided by L ratio, if H is more and more, the peak point actually keeps moving out of the diaphragm. That means you have to put the resistors outside the diaphragm. So key thing that I am trying to point out is, if the pressure is 1 bar or 2 bar, you make a thin diaphragm, you can put the resistors on the diaphragm itself. That is where stress is highest. Outside the diaphragm, there is no stress. But if thickness becomes more and more, the stress actually goes outside the diaphragm also, and the peak is in outside. So your resistors will are put outside the diaphragm. Next slide. Next slide. See, you can see this is the diaphragm. Now you can see the distance where the peak location is there, it becomes larger and larger. 120 microns away from the edge of the diaphragm, 120 microns. That means it is on the anchor itself, you have to put the high pressure. Okay? And if the thickness is smaller and smaller, L by H becomes larger, and you can see the horizontal line, that high stress point will come inside the diaphragm. So difference between the low pressure and moderate pressure and high pressure sensor is moderate pressure, resistors will go inside diaphragm, higher pressure, resistors will put outside the diaphragm because the stress is maximum there. Next slide. Okay. See, next slide. Yes. Okay. So this is the stress versus pressure applied. Okay. So this will be stress is like that linear. If I put the resistor outside, and I'm talking of 1 megapascals, that is 10 bar pressure. Okay. If I go to even higher pressure, that will move even outside. So the only thing that I'm pointing out is that resistors are not on the diaphragm, outside, the resistors are very thick compared to the dimension of the diaphragm. Next. This is actually a picture composite layer. You can see the violet is the diaphragm, and these are the 4 resistors which are put there. In fact, resistor is here. These are the connecting leads on the metal taking outside the diaphragm. These are inside the diaphragm. 4 resistors are put. This is actually on chip. It looks like that if you take a picture. Diaphragm, resistor, metal, aluminum. And these are the bonds, pads on which you can bond wire. You have to actually dice it. The red line is there, cross. You have to dice it and then separate them. And then, next slide. Next. Okay. Now you see the diaphragm on this process is first we put a P plus layer. All these are P plus because resistance will be terminated by heavily doped regions, P plus region, so that when you put a metal contact onto the P plus, it becomes OB. So these are the P plus regions, and on the edge pads are there. That's on the anchor. Next slide. You can see the resistor is put on. Yes. Now you can see these are the pads, thick, heavily doped regions. Then these are the lines which are between them. Two are the resistors, which are connected in series to achieve higher resistance. And the diaphragm is somewhere here. Okay, the ones at the edges, they are outside the diaphragm. The ones in the four devices you see are inside the diaphragm. Okay, next one. Now you put metal. Yes. Now you can see resistor, E plus region, and the metals. All of them are there connected together. This is outside the diaphragm. Just in case you need to monitor some resistors which are not subjected to stress, they are there. Are you able to see a cursor by any chance? No. Okay.
No, sir.
Okay, so this is the device where you see four resistors. You can see actually 4 into 2 because two of them are connected in series. The pads are connected together to increase the resistance. Next slide. Okay, you look at the back side of the wafer. It will look like this. In fact, you can see the portion where it will be anchored. The back side is here. This is the diaphragm. What you see is the diaphragm. You see a portion there, the edge, that is the shadow of this one. When you take the picture. So you see the diaphragm on the back side, resistors are either inside the diaphragm or outside, depending upon pressure. Low pressure, it will be within the diaphragm. Very high pressures, 400 bar and all will be outside. Next slide. This is actually the photograph of the device, fabricated in that sense. Okay, so you can say final mask when you do, all these white things are the aluminum, and dark are P plus, other things are resistors. You can see two resistors connected in series. Okay, next slide. Then you want glass on the other side. This is actually the photograph of the full wafer. I hear some shouting. So you can see that the edge, bottom, there is a flat in the wafer to show the orientation. Next. Okay, this is actually after you dice it. Can you go back one? Can you go back to the previous slide? No. Yes. See now you can see the lines in bringing. There are the lines where you dice the device using a diamond saw. Cut the hole to realize the chips. Next slide. Okay. This die is mounted on the header. You can see the glue where it is mounted. Then the wire connected to the port. There are 4 wires connected because there are the bridges. You can see the and this color is due to the oxide. This is the resistor. Okay.
Next slide, sir.
Next slide, please.
Yes, sir.
This is actually very high pressure sensors, which is packaged. In fact, courtesy Professor Nayak, who was in ISRO, he is also with us. He has been active participant on this device packaging. And this is the chip, silicon chip for the high pressure, whatever. And that is mounted. Okay, 1 minute. Just 1 minute. Oh. Go back. Go back. You can see the, when I touch it. Yes, forward. Okay. On the top right corner, you can see there is inside the package there is this chip that is very small. The package becomes so big. Next slide. This is the measured characteristic of the device. Pressure versus output voltage, 5 volt supply voltage. You get at the maximum 400 watt. You get about 200 millivolts output for 5 volts. Linear, you can see. That means the deflection is small compared to the thickness of the diaphragm. Next slide. Okay, now I take you on to the on-chip integration. This actually was done by some of my students when I was in IT Madras, way back in 2005 or more, like that. At that time itself, we were working on the devices. See, this left-hand side, you can see that is actually the bits and bits. They are actually laid out on the diaphragm. Okay, they are piezoresistors on the diaphragm. And these resistors are RD1, RD2, RS, etc. I hear some noise, etc. This is the differential amplifier. So this was done deliberately. So on the same chip, you can put this piezoresistor, you can put the diaphragms on the chip, you can put the resistors on the diaphragm, and also outside the diaphragm, I'm sorry, the differential amplifier. There is some lot of noise. Okay, that's clear. So amplifier and the piezoresistors on the diaphragm and outside diaphragm. Amplifier is outside diaphragm. Okay, this I think all of you are familiar. Differential amplifier. It's a MOSFET transistor. That's why I put that symbol. So MOSFET relies on the outside diaphragm. That's like that.
I change it, sir.
Yeah, this is actually the wafer. See, on the left-hand side, there is no diaphragm right now. When you finish, you do all the processing for these resistors which will go into the diaphragm, and also for the source drain regions, N plus regions, and also the load resistance, everything you put. It's a cross section. Now, once all this is fabricated on the top with the standard integrated circuit technology, all the resistors are now no diaphragm. Now, to realize diaphragm, just like this. You have to H. No, only one. Jump to 2. No, go back. Okay. See, now, go back, go front. See, I'll stop. See, I showed two. One of them is that angle, one of them is vertical etching. The angle which one you saw is by wet etching. That is potassium hydroxide solution. You put potassium in the front side, you put it in the KOH etching, it will make that angle at about 70 degrees to the surface. But in our place where we did initially, we were using KOH etching, 30% KOH etching, which attacks silicon and etches. It is good. Can you go one slide backward?
Yeah, sir.
Yes, see, this is the angle, 70 degrees. That is the plane which is one plane which does not get attached by KOH. So this angle, you have to open the window here, depending upon how much is the diaphragm width you want, depending upon thickness of the vapor. So this is the wet etching. Today, nobody likes sodium and potassium in the clean rooms. Reason? Sodium if it's or potassium are, these get ionized very easily, even if little bit of moisture. And those ions will do like anything when you apply electric field. So, and if there is ions moving in the chip, it will be instability. So that's why most people are debarred from VLSI when they were using this technique. So people came up with the deep reactive energy. Show me the slide.
Next slide, sir.
This slide. Here it is brute force. Oh no, only one side. We have jumped to 2. Keep it there. So okay. Now you can see this is vertical. This is etched in the gas phase. This is permitted in the along with the VLSI. So you can do electronics, you can do pressure sensor. Wherever resistors, piezo resistors are there, you're etching in the back side. This is using SF6 gas. What you do is etch with SF6, which etches silicon, little bit, then coat with a polymer using changing the gas. So alternately, SF6 and another polymer gas, you alternately change into number of cycles, you get vertical. So you get vertical cavity like this. So this is the cross section of the finished device. Let's go back. Go to front. No, further down.
Next addition.
Next. No, you're going back, I think.
Okay.
Go forward. Next one. This is one. This is what is put on the top. So no, don't change. See, there is one square on the left hand side. Unfortunately, I'm not able to show it here because I'm not projecting. So there's a rectangular. It's not a square, rectangle is there. That is the diaphragm. On that you see 4 resistors on left side. That is actually piezo resistors connected in the form of bits on which. To the right side, the whole entire right side, that is the electronics. You see the MOSFET, green color, that is the source, drain, gate. Then above that there are 2 resistors are there. And below there is 1 resistor. That is 2 transistors with 2 resistors as load and 1 resistor at the bottom. That's what we saw. Just go back.
Back, sir.
Just to show the words resistor. One more. This is the thing. This left hand side portion is on the diaphragm. The right hand side, the whole thing is on the outside the diaphragm. Go forward, please.
Sir.
Yes. Next. Yes.
This one.
Picture which you are showing, all the blue lines are all the metal, and all these shaded portions, etc., are the diaphragm. On the right side, there is no diaphragm. Okay. So this is all top view. This is the diagram. Mask actually. Next slide. This is actually the picture taken on the wafer. You see the lines, they are the line which you strike, and each square is one chip. There is the piezo resistor and the amplifier. So here you can see 1, 2, 3, 4, 5, 6, 6 into 4. 4 devices you see here. Now, how do you separate them? Dice.
Hello, sir. Unmute yourself. Hello. Sir. So unmute yourself.
Okay. No?
Yeah, sir. Clear. Audible, sir. You can continue.
Okay. Okay. So I think it's went by itself to mute. So now, you heard previous things? So this is actually in which each one is one chip between the squares. So which has got the sensor sitting on the diaphragm, outside diaphragm, this amplifier. Now we have to dice this. These lines are there, vertical and horizontal lines. They are the scribe lines provided in the wafer. You dice them using your diamond saw running through that. What are they? Next slide. This is the one chip that you saw. There are 24 chips are there. When you dice it, I magnified it. This is device which has on the left hand side you have got the sensor, on the right hand side you have got the amplifier, differential amplifier. Okay, so this is actual photograph of the device taken, fabricated by 2 of my master degree students. Both of them are tapped off to UC, leaving me behind. Okay. Yes.
So next slide, sir.
The next slide. This is the same thing I told you chip. When in the previous slide you saw the whole thing amplified one chip. This is a chip actually. You can see the I don't know whether you can make out. You can see the whole chip there. Around that you can see the white region where the glue is put. And this is the cap was put earlier, the cap was cut. Because we had some problem we wanted to see, we cut it this one. So this integrated pressure sensor chip, and you see the wire bonding coming onto the post. Next slide. Okay. So what you saw previously, onto that this cap is put. In fact, what I had done was, this cap was earlier there, I have cut it to show. So this is a pressure port. So this will be connected through a jig to the pressure port, a gas filter, or whatever you want to do, where you want to monitor the pressure, you can connect it. Okay, so the header and the pressure port. Next. This is actually the result. The result. You are able to hear me?
Sir, continue.
These are the results. You can see, you can measure the voltage right at the sensor output, that is the bottom curve. And it's an amplifier gain of about 5 was designed, 4.5 has come. That line amplified sensor output. It shows that it's a device which has been working, and this is the project done by the students. In fact, now this only to demonstrate that you can integrate pressure sensor and electronics. Next slide. Next. Okay, so we have seen what I showed now, previous slide. What I had shown earlier was actually a sensor which can go up to 10 bars pressure. Now this is the pressure sensor for low pressures, like ICP and all those things. When you want to make, you have to go to low pressure, 120 millibar or 600 millibar. Next slide. Next slide. So I'll show you two. No, go back. Okay. See, the left-hand side one is the flat diaphragm. You put the resistor inside diaphragm. When you go to low pressures, okay, you have to make diaphragm thinner and thinner. To make it thinner and thinner, H is smaller and smaller. So W0, deflection by H becomes variable to H. So then nonlinearity comes into picture. That is, as you vary the pressure, output voltage will not vary linearly. That's the meaning of nonlinearity. So, but you change the structure. Use a sculptured structure. Okay, you have here, for example, same thing. The diaphragm is the same. Only thing is, instead of flat diaphragm, we have a diaphragm which is having the boss structure coming. You can see the hanging things here. So I'm not able to show here. Okay. So on the top, you can see in the left-hand side figure, there are 4 resistors mounted parallel and perpendicular to the diaphragm, dotted line. Here, there are 4 resistors. 2 of them are the edges. They experience transfer stress. Okay, transfer tensile or compressive. The other one will get middle one too will experience if this is transfer, the middle one gets compressive. So that means 2 of them will increase, 2 of them will decrease. Same principle. All that we are doing is we are providing extra support which prevents that too much of deflection. That is called the boss. The boss is controlling the deflection. Okay. Or structural deflector. Next slide, please.
Yes, sir.
Okay. So this is the flat diaphragm. And this is to show that there is a lot Next slide. Next slide. Hey, unmute or something. Okay. Now you see, if you change it to like this, this is actually a thing which has got chip size is 300 by 300 micrometer and diaphragm size. One end to other end is 200 by 200. Diaphragm thickness is 25 microns. There are boss structures here hanging out. You can see the bottom, they are not all the same line, so that the middle portion can move up and down. Okay, this is 200 micron, same diaphragm. Chip size is 300 micron, size 300 micron. Diaphragm is 200 micron, 2000 micrometer square. Within that, you have got this boss. Right?
This one, sir.
So this is the result that was obtained. It's here in IAC only is not declared. Flat diaphragm thickness is 25 micron. Sculptured also 25 micron. Okay, when you subject it to that particular stress, 1 bar or so, the 600 millibar. Okay, the stress is more in the case of flat diaphragm, and stress is less in the case of sculptured diaphragm. Output voltage is more in the case of flat, output is less in this case of sculptured, but linearity is much better in the case of sculptured, because we want linearity better. Output is less. We don't care how we can put it on. Okay, so we are targeting linearity for this application. These are useful everywhere, many places, biomedical applications, etc. Also, mostly biomedical applications. Okay, next slide. Okay. So this is actually to show the cross section of the device. That top view, you can see the boss, that big thing, hanging thing, and there's big diaphragm there. And cross section you take in the dotted line. This is a glass you want, and the boss which is there in the center, two boss are there. Okay, they can move up and down when you pressurize, and the red dots in the top are the resistors. On the top diagram, you can see the top view where the resistors are put up parallel to these edges, so that they are positioned in the correct direction. This glass is bonded so that you can create vacuum and bond the glass. Okay, you can whole device is fabricated like that. You take the whole wafer, burn glass out of that. Okay, apply voltage. Then there is from the glass the sodium atoms move, and there is an electrostatic force created. It gets bonded in very strong bonding in there. So that is glass bonding. This is another technology we use.
So next slide.
Next slide. Okay,
Yes,
this
sir,
is the
sure.
distribution. One is using transverse, one is longitudinal. Now both are transverse, one is one direction. This is so that the stress in the two resistors at edge is in one direction, and the center is in the other direction, so that one of them increases the other, the center to the, so that you get an output voltage. Okay? This is actually a simulated result. So you know where to keep the resistors. COMSOL simulation, you can simulate the structure in that, you get this particular plot. These are not measured stress. These are estimated. In fact, whether it's correct or not, we know when we get the output to almost dictated by this pressure. Okay, next. This is looking at the backside of this chip. I don't know whether you can make out. See, this is the boss is the one which is protruding out. The diaphragm is on the top other side. Okay, so you can see boss means that is where between the boss there is a space. That's where on the other side, back side of that, you keep resistor. On the two sides of the boss, there is a gap. That's where the diaphragm is present. Two resistors. Okay. Next slide.
This one, sir.
Okay, now this is a picture of the device. The white that you see is aluminum. And the four sticks like thing, R1, R2, R3, R4, they are the resistors. So where you see R1 and R3, the edge structure portion is there, thin diaphragm. And at the R2 and R4, there's a thin diaphragm in between the two bosses. So between these two and R1 resistors, there is the boss. Okay. After all that is done, you can see that resistor is there, and there is a darker edge at the edge, that's the P plus. So that I can put metal, that green, that's the white line, onto the P plus. I can, that's otherwise then it makes only contact. So this is the structure that you get here like this. So it's not just for the sake of showing. You can see outside the diaphragm, this is all diaphragm. Outside the diaphragm, I put some resistor. In case I need to make some compensation while using, add somewhere outside some resistors, I can make use of that. That is the idea. Next.
Yeah,
okay.
sir. Thank you.
Now here comes. You can see the R1 and R3 resistance go up because of the location like that, because of the transverse stress, transverse tensile, as if it's widening that, so the resistance goes down. R1 and R3. And R2 and R, these two are in the middle getting compressed, so resistance increases. Transverse compression. So you get a resistance bridge like this. These are photographs of the devices fabricated in our sets. Okay, so this is useful, used in the helicopters and all that. We are selling them to them. I don't know how much money. So this is a picture of one device and there's a structure there. Okay. Delta we have a restraint, that's the case factor. Next slide.
Next,
This
sir.
is going back to that chip mounted on a, kept on a petri dish. Okay, big one. And you can see how many devices are there. There are at least some 300 devices are there. You see some places you see there's a gap. In the chip, in the wafer, you see something is removed. Those places are the places where at least 4 devices have been picked from here at the time. At the time it's the photograph, there are so many devices are there, but there are 4 or 5 devices have been taken away from there for packaging, etc. Okay. So after this, the header, package, and all the things. I'm not talking about. Yes, next slide.
This one, sir.
That is the result pressure. You can see it's gone up to 600 millibar, 0.6 bar below atmosphere. There is some offset voltage there, but the output is linear with respect to pressure. You get about 250 millivolts for 5 volt input. Okay, 600 millibar sensor used in the helicopter and all that. You can use some other application also. If you want to use an ICP, you have to go down to 150 millibar pressure. Okay, this offset voltage is there. That can compensate by using electron output. Okay.
Next slide, sir.
Slide. Okay. This is, I think, the amplified view of that. This is 1.2 bars. 1 bar and above. And this is not subtract, it's other. So linear. This is flat diaphragm. Without a there is offset voltage. This is because There will be some resistance change, even if it's a few ohms, it will show up as the support. This is 150 millibar. Okay, so this is just a result that I'm showing, linear result. So for that, you have to adjust your dimensions of the sensor or the required pressure. The structure also you have to. Yes, just like this. I'll very cross door. Next.
So next keys and okay.
Yes.
Yes, sir.
Stock is complete now. Unfortunately, I was actually connected. Are you able to hear me?
Yes, sir. Yes, sir. Yes, sir. No problem, sir.
Oh, that's slow, I think.
Shall I stop this screens here, sir? Shall I come to main?
Yeah. You stop.
Yeah, sir.
Yes.
Professor BPR, sir. Hello.
Yeah.
I'm not
Yes,
able to.
Professor HBK.
Yes, sir.
Professor K. But sir, thank you
Video.
very much, sir.
Just 1 minute.
Professor Bhatt, sir,
Video.
thank you very much for
Wait,
your
wait,
enlightening talk on pressure sensors. It's time for few questions. It is time for few questions. Participants, if you have questions, you can directly ask. Unmute yourself, you can ask the question.
Yes.
Please unmute yourself and you can ask questions.
Means everything is either understood or not understood.
It was very good, sir. I mean,
Sir, some questions are there. Hello.
Okay.
Gray color patches and these are moving over slides also.
Go back to.
So gray color patches and these are moving over slides also.
1 minute, 1 minute. There's some. Yes.
no, that is not a question.
Question.
That is
Okay, sir.
question. Okay, that
Okay,
was,
sir.
yeah.
I didn't hear the question.
Okay, sir. I think no questions, sir.
No questions.
BPS, sir. BPS, sir.
Yeah. So, Professor.
Yes, sir.
Sir, I have a question, very general one at that. Now that you have been a teacher for 50 plus long years as a teacher, first at IIT Madras, then now at IISc Bangalore, can you please share with us how teachers can be very effective in their teaching and research?
I think today I was not very effective because I was not able to, I didn't have control of the slides. Okay.
No, sir, the online platform has its own limitations.
I know.
And there are network issues and all that.
Okay.
So that apart, in general, I would like to ask you, sir, so that you can share your experiences with regard to teaching as well as research, how our teachers can be more effective and contribute towards
Yes. I can tell you.
Quality technical education.
Yeah, see, when you go for the teaching. Hello?
Yes, sir, you're audible. Please go ahead, sir.
Main thing, of course, I don't have to tell you people because first thing is you have to be thorough with what you want to talk.
Yes.
Because then you don't read just one book or anything, you may read also journals so that you know what is going on around, particularly for a graduate level if you are teaching. You must go through those things, upgrade yourself, and you must be prepared for whatever doubts are there. You should be able to handle. Otherwise, if you are not able to handle, you should not feel sorry or cut up. You can say, I would come back to you tomorrow and clarify it. Because there are human beings. Maybe that day you might have had a blow. So what is the preparation? And also we have to give the slides. If slides, give the slides to the students so
Yes,
that
sir.
they can come back to you with questions. In fact, I used to have a very good experience with the students in IT Madras and IAC also. They used to come back with doubts and get this clarified. That way,
Yes.
it is a good learning process, both for the student and the teacher. And the teacher, if he says, I have learned everything, I am bluffing. Because by teaching itself, I have learned quite a bit. Yeah. Okay. So
Yes,
Harish,
sir.
I think I taught
sir.
you, I don't know what course, devices course, I think.
Yeah, I mean, yes, sir. We will keep your advice in our mind, and we will definitely do our best. And
Okay.
thank you very much, sir. So now, on behalf of the Department of Electronics and UVCE, we thank Professor K.N. Bhatt for his wonderful exposition of the pressure sensors, MEMS pressure sensors, and the pressure levels, low pressure, medium pressure, and high pressure, and various issues associated at different pressure levels, and how and the kind of trade-offs that are so very important in the design. So thank you very much, sir. Once again, thank you for your time and your effort at this very ripe age, and getting yourself familiar with the new technology yourself, and then with regard to the online teaching. And we are extremely delighted and very fortunate that we have had a professor of such an eminence with so much of experience and in teaching.
Let's have the fastest bowler say bowler.
So thank you very much, Professor Bhatt.
Thank you for
Thank
the
you.
opportunity.
Thank you, sir.
Thank you.
Thank you, sir. Your eye-opening session. Thank you, sir.
Thank you.
Thank you very much.
Rose?
Yes, sir.
Okay.
Well, with this, we will end the meeting.
Okay, sir. The participants are requested to join 11:50
You
a.m.
want to start
Thank you.
video?
Sir, schedule an ND meeting, sir. BPR, sir.
Yeah. Please enjoy.